functions and graphs, R.5. It deals with nonlinear functions, and models. Meaning situations from the real life situations that use these functions, nonlinear situations. Okay, so let's start with the quadratic function. The simplest quadratic function that we can think of is x squared. I am hoping, and you'll stop me if you need any explanation here. The graph of this, the most simplest function that is quadratic is this. So this is y, or f of x equals x squared. Now we can have all sorts of combinations and transformations on this function. So I don't know if you remember what happens when we graph x minus 2 squared, or what happens when we graph x plus 4 squared. So these are horizontal shifts. In this case, the function is moving to the right 2 and keeping its shape with no change. So this is x minus 2. For x plus 4 is a horizontal shift to the left 4. Same shape, no change. So this is x plus 4 squared. So this is a horizontal. Both these two are horizontal shifts. Okay, we also have vertical shifts. So if I want now to graph, let's say, x squared minus 3, or x squared plus 4, here's what's going to happen. I still graph what is called the base function, which is x squared. And this is a vertical shift of 3 down 3. Same shape, no change, x squared minus 3. And this one is an upshift of 4. So this will be x squared plus 4. So these two are called vertical shifts. And what else I should mention here is reflections. Reflections. Based on the same function, we are talking about still f of x equals x squared. The only reflection that I can present here is what is called negative x squared. Because if I change x with negative x to try to reflect with respect to the y-axis, is not going to make any difference. But this is a reflection with respect to the x-axis. Reflect, WRT, with respect to, that's how lazy people write WRT, with respect to the x-axis. So here's again the graph of x squared. And the graph of negative x squared will be this. It's reflected with respect to the x-axis. One last transformation that I would like to mention. Stop me if you have questions, please. Any questions? Anyone? Okay. Our stretches, vertical shrinking. So vertical stretching, shrinking on the same function. We're still talking about x squared. So there are two options here, like let's say 1/2 x squared, and the other option, let's say like 3x squared. Let's see what transformations, what do these do to this function. So if I graph again x squared, here's x squared. Let's see what happens now when I graph 1/2 x squared. You realize that this number will divide all heights in 2. So now the graph will open up. So it will be something like this. And this is exaggerated, but this is the point I'm making. All heights are divided by 2. I exaggerated a little bit more than I should. Now this one multiplies all heights by 3. So it will look kind of like this. So this is 3x squared. It's a vertical stretching of the graph. This one is a vertical shrinking of the graph. Opens up more. So these are the vertical stretching and shrinking. These.
So 1/2 is the stretching and 3 is the shrinking.
3 is the stretching. 1/2 is the shrinking. And I can show that also with the calculator, because maybe it's better if you'd like to see those like that. So if we should graph x squared first. The next one like 0.5 x squared. And the third one 3x squared. And now watch, because these newer calculators, you see they have 3 different colors, blue, red, and black, and they will follow shortly. However, I will change the viewing window to the standard viewing window, or I can create even a nicer window, like between, let's say, -6 to +6, -2 to 10. So I'm going to do that, -6 to +6, with a scale of 1, and -2 to +10 with a scale of 1. And now watch, they will be in this order. X squared first, 1/2 x squared, and then 3x squared. Ready? Here comes x squared. Here comes 1/2 x squared. As I said, I exaggerated a little bit. And here comes 3x squared. So 3x squared is stretched. 1/2 x squared is, the graph is uses a shrink. I mean, we applied a vertical shrinking of the graph for the red one. And the middle one is, of course, x squared. Now, if you ask, why do I need to think in terms of transformations? These are all these are called transformations on a function. Why do I care about horizontal shifts? Why do I care about vertical shifts? Why do I care about reflections? Why do I care about vertical stretching and shrinking? Here's why. And let me give you a combo. And you'll see how easy it is and how quick you can graph the function and you understand it better. So if we look at, let's say, f of x equals -2 x plus 1 squared and plus 4, in order of operations, So about that. So the order of operations requires us to graph the function first. So that I graph x squared first. Here's x squared. The next step has to be a left shift of 1. Okay. Here it is. So this is x plus 1 squared. I should have written here x squared. Then I have to stretch the graph by a factor of 2. Fine. I'm stretching the graph by a factor of 2. So this one is 2x plus 1 squared. Then, of course, I will flip the graph. Here's the flipped graph. The negative 2x plus 1 squared. And now the entire graph moves up 4. 1, 2, 3, 4. Here's the graph. So this is the final graph. It may not give us the exact x-intercept and y-intercept, because it doesn't. But I know for sure that the vertex of this parabola is negative 1 comma 4. And I didn't need any calculations. I can do this mentally and say, oh, I know, it opens downward because the leading coefficient is negative. It has a vertex, which is the max min only for a parabola. No other function has a vertex in the sense of a max min. But the parabola, which is the quadratic function, and I use transformations. Yes, if you ask me, now find the x and y intercepts, I'll say fine. But I can find the domain and the range in a blink. Can anyone give us the domain and range for this function?
Is it negative infinity to infinity?
Great job. And what about the range?
Is that 0 coming from you?
Okay, so let's talk about the range again. So when we talk about the domain, we sweep the graph from left to right. When we talk about the range, we sweep the graph from below to the maximum possible value where the function exists.
4 and negative infinity.
I have to start with the low. For the domains, I start from left to right. For the range, I have to start from low to above.
So negative infinity to 4.
Excellent. Great job. And now if you say, find the x-intercept, and find the y-intercept, I'll say no problem. The y-intercept is the easiest, in a way, because I have to plug in 0. And f of 0 is, let's do this together, 0 plus 1 is 1, 1 squared is 1, 1 times negative 2 is negative 2, and negative 2 plus 4 is 2. So 0 comma 2. Yes, I have to adjust the graph because it crosses here, but I have the picture in my head. That's not an exact graph. That's what I'm saying. That's why algebraically we can determine the x and y intercepts. So now the x-intercept is when y equals to 0. So I have negative 2, x plus 1 squared plus 4 equals 0. I see that the function has to have two solutions. I mean, the equation has to have two solutions. It crosses the x-axis twice for sure. So I will move forward to the other side. I will divide both sides by negative 2. And then take the square root. Apply the square root to both sides. So then I get x plus 1 squared equals 2. I take the square root and get x plus 1 equals plus or minus the square root of 2 and subtract 1. So what are the x-intercepts? Negative 1 minus the square root of 2 comma 0. And negative 1 plus the square root of 2 comma 0. These are the x-intercepts. Which I could have not determined with a quick graph using transformations. All these transformations are applicable to any function. They're extremely valuable. Extremely valuable. We're going to use them for all functions that we're going to look at. But not before we look at, I want to refresh your memory on the quadratic formula and graph something like this that does not have the square completed, like the one that I just showed you. So you can choose any function if you'd like, or I will choose any quadratic function from 17 to 24. I selected 20. I have no preference really. Anyone would like to pick a quadratic function or make one up, or you're fine with 20? Okay, 20 then, on 64. We have y equals negative x squared minus x plus 6. Well, the trick, the steps that I used here are not working here, because the square is not completed. So I can, unless I take the time to complete the square and present it like this, but I don't want to do that. I want to show you the other way as well. So there is no need to complete the square. We have a different step-by-step method of graphing this. Okay, so first of all, we start with number 1, which is the shape. I know it's a parabola, but I don't know whether it opens upward or it opens downward. Well, a parabola that has a minimum has to have the leading coefficient positive. A parabola that has a maximum, it will have a leading coefficient that is negative. Did we have an example from each? Yes, we already did. This one had a positive leading coefficient, 1. This one had a negative leading coefficient. It has a maximum. Good. So I identify this is in the correct descending order. I identify the leading coefficient as being negative 1, so this is our case. The parabola will have a maximum. In step number 2, I have to find the vertex. The vertex can be a minimum or a maximum. In our case, it's a maximum. The vertex, like any point, has 2 coordinates. The x of the vertex and the y of the vertex. Anyone remembers how to determine the x coordinate of the vertex? Anyone? The x coordinate of the vertex. Okay, I'm going to come back to it in a second. I just want to refresh your memory. When we solve the equation ax squared plus bx plus c equals 0, notice everything in descending order, everything on one side, equal symbol and 0. This setup is mandatory for the quadratic formula. Can anyone refresh our memory on the quadratic formula? Anyone remembers it? Don't be shy, it's okay. I'll help you. Anyone? Okay. So it's negative b plus or minus the square root of b squared minus 4ac over 2a. So these go together. So what's all this? Why did I jump from the vertex to this? Because I want to make a point. This is the x-coordinate of the vertex. X of the vertex. So I would like you to memorize them together. If you know one, you should know the other, hopefully. So this is negative b over 2a. Now, how do I determine, let's determine negative b over 2a, but how do I determine the y coordinate? Once I have the x coordinate, how will I determine the y? If I have this, let's say it's 3, how do I determine the y coordinate for the same function?